G'day and welcome to L22 thin lenses and combinations. Sometimes you'll see it L22B, it's the same thing. If you see something with L22B, it's the same thing as L22. We're looking at some thin lenses and forming some images, and we're going to be using some different kinds of lenses and putting them together in different ways and seeing what sort of images get formed from that. Now, we're looking at using three different lenses today. We call them lens A, lens B and lens C. Lens A is the fat one. You get a little close up of that. Lens B is the flatter one, like so, and lens C goes like that one, looks like that, and they're labelled so you can see. So we're going to be measuring the focal length of each one of those lenses today, and lens A, we're actually going to measure the focal length of that using four different methods. Okay, all of these methods here. So I'll take you through those in just a moment. So we're going to use four different methods. The first one is we're going to use the distant object method, and it looks very much like this actually. We're going to get a distant object that's well lit. We'll get the rays coming from it and try and focus an image of that object, and then the distance between the lens and the focal point should be the focal length of that lens. This is quite rough because that's not necessarily parallel, but it gives you a rough idea of how much the focal, or how big the focal length is going to be for your lenses. So when we do it more accurately later, you'll have a good idea of where to start. Let's do that now. Okay, so what we're going to do is we're going to use our distant object. Actually, I'm going to use the fluorescent light, which is above me. It's maybe a couple of meters above, maybe not even that. So it's not really a distant object, but we're just getting a rough idea. If you do this on the floor, it might actually even be a better answer. But we're going to get the light rays from that distant object to come down through the lens and try and form an image. I'm going to use the table as a screen, like so. And if that's a converging lens, it should converge those rays, and it should form an image roughly on the focal point. Because our object is distant, that should be roughly the focal length, and you can read that from the scale. So when you're doing it for yourself, you can get yours. There's some little differences between the lenses, so it's not necessarily going to be the same measurement as this, and this is rough anyway. Just you can see where lens A is. If you do that with lens B, it's flatter if you start from a distance, and you, oh look, already you can see that the sharp image is being formed with the lens much further away. So you can see lenses A and B have quite different focal lengths. If I try to do that with lens C, I actually can't do it because those rays are being diverged apart from each other. You can't actually form a real image with real light rays that focus on a screen. So this is only a useful method for the converging lenses. The next method you're going to use to measure the focal lengths of the lenses are the auto-collimation method. Now, auto-collimation, auto means self. A collimation means a column or a beam of parallel rays. So these rays that we used over here, that are parallel rays, that's a collimated ray, a collimated bunch of rays. If you have a ray that comes from the focal point, it should come out parallel like so. Then what we're going to do is actually place a mirror, a flat mirror, and it's going to bounce those light rays back so that they enter the lens parallel, so they should backtrack along themselves and come back through the focal point and form an image right back where the object was. So once we've got that sharp image formed there, then we'll know that this is right on the focal length, and we can measure again our focal length from here. We'll just show you the equipment that you're going to use to do the autocollimation method. We've got the object is here. It's a little mesh. It's a triangle cut in a can with some mesh behind it so that you can focus on that. There's a lens holder and a saddle. We've got it on an optical bench to make it all nice and professional looking. We've also got a mirror on here. If you flip that around, we can use that as a screen. So in this part we're going to need the mirror, so we want the mirror facing this way. And we'll start off with using lens A for our autocollimation method. We can put it in the lens holder. You can tighten it if you want to, like so that it doesn't fall out. Do be careful with the lenses, they can chip quite easily if you drop them. We'll need some illumination on our object. We've got a light bulb in there to make it look a bit brighter. Now just be a little bit careful, some of these, the cans that they're in can get quite warm and some of them get quite hot, so don't touch that, particularly after it's been on for a while. Now what we're trying to do is to get the objects to be right on the focal point of lens A. So I'll know if that's true. Actually, firstly I'll probably need to just level up, try to get the centre of the lens as close to the centre of the object as you can, so that we've got all our rays travelling horizontally. Same with the mirror. Okay, to set that up behind lens A. So what should happen is if I move lens A in closer and carefully, what I should end up seeing is a sharp image on the screen. Sometimes it helps to have the mirror up nice and close behind. Now you might just be able to see a bit of an image forming, and you can see it's an upside down triangle on that one. So that's what we call an inverted image. If the image is upside down, we call it inverted. Try and get it at the point where it's just the nice and sharply focused. To my eye that looks reasonably well focused. If you like, you can move the mirror side to side a little bit. It shouldn't matter how far away the mirror is. If it's up close it tends to be a bit brighter, but it shouldn't change the focus very much. So it's not critical where the mirror is, but closer is better. If you want to shift the mirror sideways, it might give you a better view of your image, so that can help sometimes as well. And you would measure your, if that's in proper focus, okay, if that's well focused, then that must mean that the object is right on the focal point. The rays coming out the other end are parallel, they're going back in parallel, and they're meeting again at the focal point. And so you can measure the focal length to be from the surface where the image is being formed and the centre of the lens. Now that can be a little bit tricky. It might help to move the mirror out of the way, and you can put the ruler right up against there and measure to the centre of the lens holder is a pretty good approximation of the centre of the mirror. So do that several times and maybe even swap who's doing it so that you get different people's judgment of where it's in good focus or not. And that you do that for lens A. Then you would swap over to lens B. And also just have a glance at lens B. Have a glance at your rough measurement from the distant object method and see if your answer agrees with that. Now, what you'll notice actually, if you put lens B in where lens A was, sometimes you get a bit of what looks like a faint, sharp image there. That's not what you want. You notice that I haven't even got the mirror there, so that can't be the autocollimation method because it hasn't gone through and come back. That's a bit of a reflection off the inside surface of the glass. That does trick some people. So make sure that you've got your mirror there. See that nice bright light that comes there? And you expected B to have a longer focal length. And so you come back to the point where it's nicely in focus, like that. And then you can repeat your measurements for lens B. I think it's 4 times, something like that you have to measure the focal length for lens B. The next method that you're going to use to measure the focal length, you'll just be doing this with lens A, actually, is the object image method. So with the object image method, what we do is we put an object not distant but not at the focal length either. We want to put the object at some distance away where you can actually form a real image on a screen. If you can do that, you measure the distance from the object to the lens, then measure the distance from the lens to the screen where you form the image, and that is the image distance. And those two distances are related to the focal length of the lens using what's called the thin lens equation, which is 1 over DO plus 1 over DI equals 1 over F. DO is the object distance, DI is the image distance, F is the focal length. Okay, so now we're going to actually get the focal length of lens A using the object image method. Now we've got our lamp turned on and our object is nicely visible. I've made sure that I've got lens A, just check that, lens A back in the lens holder instead of lens B, because we're only going to use lens A for this section. Now I'm going to swivel the mirror around and use the screen on this side, and I'm going to put the screen about 1 metre away. There's some metre rulers around. You can get one for yourself in the lab and make it around about 1 metre difference, something like that. And I'm going to try and use lens A to form an image on the screen. So if I can get that sharply focused, I'll move in a bit closer, a bit closer. Now that distance here should be a little bit bigger than your focal length. Okay, so you won't be as close as the focal point there, but you can see I've got quite a nice sharp image, and it's a good idea to get a couple of people to maybe judge whether that's the right focus or not. You can see that on the screen there's quite a enlarged, a magnified image. If you want to get a better view of that, you might want to use a sheet of paper, and you might be able to see that the object is, the tip of the triangle is pointing upwards, the tip of this triangle is pointing downwards. So it's a real image because it's on the screen with real light rays, and it's inverted because it's pointing the opposite way to the object. So it's real, it's magnified, it's inverted, is the nature of that image. So how do you get the magnification of that? Well, firstly, before you get the magnification, you can get the the object distance in the same way that you did before, from the object to the centre of the lens. But now you also measure the image distance from the centre of the lens to the centre of the screen. And then you can use the object distance and the image distance in Formula 1, the thin lens equation, to work out the focal length and the focal power of that lens. And it should be roughly the same as you were getting for auto-collimation. If not, ask your demonstrator, check your calculation. Okay, you can get the magnification by measuring the size of the object. You can do that with a ruler. You might have some calipers or something that you might be able to borrow from the lab, and use that if you like. And measuring the size of this, again, you might need to put a sheet of paper there. It's getting a bit fuzzy at the end. It might be a case of measuring the length of 4 or 5 grid spacings on here versus 4 or 5 grid spacings on here. It might be easier. I'll leave that up to you to measure that magnification, and compare the ratio of heights to the ratio of object and image distances, and see that should roughly agree. Now, we ask you to do this twice, but with lens A, not lens B. You're going to use lens A again, but you're going to look for what's called the conjugate position of the lens. Now, if you get the object and the screen and leave them, don't move them. Okay, there's a common mistake that people make. Leave them where they are. Move the lens, and if you move the lens all the way up the other end, what you will find is that you should form another sharp image. I'm not sure if you can see, but it's also inverted, but it's now, instead of being magnified, it's diminished image. It's still real because it's real light rays being captured on the screen, but it's now diminished. So you can now measure the new object distance, the new image distance, plug it into the thin lens equation, and I'll let you guess what you should expect to see for the focal length of that. You will get a different magnification for this. Compare this magnification to the magnification that you got in the conjugate position that you got already, and that's one of the questions that you need to answer. Right, next we're going to use the secondary focal length method, or the secondary focal point method. And the way we do that is to get some parallel rays going into the lens so that they should form an image on the focal point. Now, the way we actually make the parallel rays, you know how to do, because we've done that in the auto-collimation method. But we're going to make the parallel rays using lens B. So we're going to auto-collimate lens B firstly. We're going to put in a mirror. So that when B is right on the focal point, you'll get a sharp image back here. So auto-collimate lens B firstly, then remove the mirror, and we have a collimated beam of rays that we can now use to pass through our second lens, which is lens A. and because those rays are coming in parallel, it's like it's being a distant object. They should meet at the secondary focal point of lens A. Okay, so to do the secondary focal length of lens A, we need to make a collimated beam, and we're going to use lens B to make the collimated beam. So make sure it's lens B that's in the lens holder. Get the mirror like you did before, and get a nice sharp image. It should be about the same as the distance that you got before for lens B, so it shouldn't be too hard for you to find. When that's done, you can remove the mirror and you can put lens A behind it. Like so. So now we should have parallel rays coming out of lens B and into lens A to find our secondary focal point. Just check the vertical position of all of these things, okay, so that they're all at the same level, and the bench should keep it, them all in a straight line at least. That's not too bad. So you can switch around to the screen, the white paper, and come in carefully until you get a sharp image of the mesh. You're in and out a little bit, and I think it's about there. Okay, when you've got a nice sharp image, measure from the centre of the lens to the centre of the screen, and that will be the secondary focal length. Compare it to the primary focal length that you were measuring via auto-collimation, and see if they're the same or not. In part B, we're actually going to measure the focal length of lens C. Now, we can't use auto-collimation to use for lens C to get the focal length of lens C directly, because you can't bounce them back off a mirror because they diverge apart. But what you can do is put a strong converging lens in contact with lens C. So lens A was the stronger of the two converging lenses. So if we put lens A and lens C in contact with each other, then these lenses effectively form a single lens. And the power of that combination of lenses is just the sum of those powers. As long as they're in contact, all you need to do is to add up the powers of the individual lenses. Now, you know the power of lens A because you've measured that like 4 times already. You can use the auto-collimation method to measure the total power of the combination of lenses, and then use this formula like this and work backwards to find out what the power of lens C is. In the interest of keeping the lenses in contact without lots of chips or anything, we've actually given you a little plastic collar that you can put lens A and lens C together in. It probably helps if you put lens C in first, and there's a little kind of a split ring that should just have enough friction in there to hold it so that it's like a single lens. So you treat that like a single lens and use the auto-collimation method like we used before. I would also recommend having the bulgy side of lens A towards the object, okay, because the concave surface of lens C can sometimes give you an image that will fool you. Just a bit of reflection off the front of the glass. You won't get that if lens A is that way. So you can do that. to calculate the focal power of lens C. Now, again, you'll be doing that several times, getting an average, getting an uncertainty. But because you've actually had to do a plus minus, addition subtraction calculation, you also just remember when you're doing your uncertainties, you will have to add the absolute uncertainties here at the end, not the relative uncertainties. You will need the relative uncertainties to get this one here from that before, but remember, because this is addition subtraction, you need the absolute uncertainties. There's a trap for people who are not paying attention. Now we're going to be doing part C, which is we're going to use a combination of two lenses. We're going to use lens A and lens C again, but instead of having them in contact with each other, we're going to have them separated. In this case, we're going to separate them by 5 centimetres. We're going to see what the image looks like when you put the two together. We're going to ask you actually to set the object 22 centimetres, measure this very carefully, 22 centimetres from the object to the centre of lens A, 5 centimetres from the centre of lens A to the centre of lens C, and then capture that final image on a screen and measure what the image distance from lens C is. So when you've done that, we're actually going to ask you to then calculate where that final image, what this number should be from what you already know about lenses A and C. I'll show you how to set that up first. You want to remove lenses A and C from the collar, like you had before. And with the two lens holders, you can see that there's actually a little device here which supposedly keeps those two lens holders 5 centimetres apart. We'll check that later. Make sure that the lens A is the one that's closest to the object. Just tighten him up a bit so he doesn't fall out. Lens C is the one behind, like so. You might want to also check again that the object and the centres of the lenses are roughly the same height as each other, and we now set the object distance to be 22 centimetres, and try and be pretty careful with it. Okay, I'm just demonstrating, so I'm going to do it rough. It's also a good idea just to measure, just to be sure that the distance between the centres is 5 centimetres, 5.0 centimetres, 50 millimetres. If it's not, just record what that separation is, because you'll need that number and you'll need it to be the real number. Okay, don't just use 50 millimetres because we said to if it's not 50 millimetres. Measure it and check it and use the number that you measure. So this should be forming an image on a screen, so we get our white screen out and find roughly where that's going to form a sharp image. And this might be a little bit tricky. There's quite a bit of travel in there. One way that you might do it is to say, okay, well, it's starting to look sharp there. And then, oh, actually no, that's much sharper, isn't it? Oh, that's better. Oh, that's much better. Okay. So you can see this is quite difficult to judge. There's a bit of judgment involved with that, but once you think it's roughly at its sharpest point, take the measurement of the image distance from lens C, so from the centre of lens C to the lens. You've already measured the height of the object. Now measure the height of the image again if you need paper again, or if you need to just measure several divisions on the mesh compared to several divisions on the mesh back there to measure the magnification of that image. We're going to check this distance and the magnification using the equation, using the formula. Good luck with L22.